So let's continue on with our discussion of physics here. I will throw up a homework assignment for you guys this afternoon. And I think we'll probably make that due next Friday. If that seems fair. It's probably going to be this chapter, and the next chapter will be the next homework assignment. So you'll probably have 4 of those little like 10 question things to do. Shouldn't be that hard. Anyway, what we're going to start talking about today is this concept of momentum. This is really going to start getting into the last of Newton's laws of motion that we haven't really discussed too much in depth. We talked about Newton's second law pretty in depth, right? The concept of applied force being related to the mass and the acceleration of the system. That was pretty much the entirety of the last 2 or 3 chapters. We've talked about Newton's third law of motion a bit, in the sense that you have equal and opposite reaction. When we talk about things like normal force, we're really talking about Newton's third law. The one that we haven't really talked about in depth is Newton's first law. This is the law of inertia. The law of inertia, Newton's first law, says that any object, now we're assuming when I say an object, I'm something that has mass. Any object that has a position, okay, if it's in rest or at motion, it will stay that way until something acts. I think most of the time the textbook definition you're going to see is an object at motion or at rest will continue to remain in that state unless acted upon by an outside force. That's a whole lot of words to describe something kind of simple. So the way I like to describe this initially to get the concept of inertia is, let's say that you have a baseball or something and it sits on a table. Assuming there is no strong air currents, nobody comes along and picks it up, that baseball is going to sit there like that forever. At least long enough to be forever, right? So what's going to cause it to move? Well, something has to happen, right? A force must be applied. Whether that's a strong wind gust or me coming along and picking up or pushing it or something, it's going to move. That ball has inertia. When my alarm went off this morning, I had a lot of inertia. All right, I didn't want to move. So in order to overcome the inertia of an object, we have to apply energy. This also applies to objects that are in motion. You see this all the time. For example, if somebody throws a baseball at you, you're likely to be able to catch the baseball and stop its motion, right? Obviously, it's in motion as it flies down the field or from the pitcher's mound to the batting box to the home plate. It's got some motion. You can stop this motion by applying an outside force. What that outside force is, maybe a bat hitting it, maybe catching it with a glove or something, but it's going to stop that motion, right? You're trading energy. So you can already see that this concept of inertia is very closely related to energy. So we need a way that we can talk about the energy required to change the state of an object inertia, whether it's moving inertia or rest inertia. We know there has to be some sort of energy applied. That energy is what we call momentum. So we need to think a little bit about how we might calculate this. So as you know, if you've been paying attention here, that whenever I introduce a new concept to you, before I just give you the formula, we want to think about where that formula comes from. As you saw in the last test, it is far more valuable for you to understand how the equations work and what they represent, rather than just to memorize them, look them up, and plug a bunch of numbers into them. Those last couple of problems I gave you on the last test, you couldn't do that, right? You had to really understand how it worked. So we're going to do the same thing with momentum. So if we think of momentum as the energy that we require in order to change the inertia of the system. If we imagine our spherical cow in a vacuum, so morphology doesn't matter, friction doesn't matter. To an extent, mass doesn't matter other than it has mass, right? So if we take our spherical cow in a vacuum, what are the factors that are going to affect how much energy is required to make this thing move? Well, you can just kind of visualize this on your own, right? If you had a spherical cow, that would be really cool looking, and I would love to see it if you have pictures. If you tried to move the cow, you're going to have to apply a bunch of force. The amount of force you're going to have to apply is certainly going to be related to the mass of the spherical cow, right? The heavier that thing is, the more force you're going to have to apply. It's the difference between, if you go bowling, it's the difference between throwing a 5-pound bowling ball and a 15-pound bowling ball. There's far more mass in the 15-pound ball than there is in the 5, and thus it's harder for us to throw. We know from our previous discussion that really is a work energy thing, right? We need to do work to apply that amount of energy. If we further recall that energy is related to mass. So it makes sense that the amount of energy we would have to apply to overcome inertia, since inertia is dependent at least partially on mass, that whatever this force is that we have to apply is going to be dependent on mass. So bigger cow needs more energy. The other thing that is going to matter to us in doing this calculation and trying to quantify this is going to be velocity. In other words, how fast do we want the cow to move if it's at rest? Or how much force do we have to apply to stop the cow from moving? This is the thrown baseball problem. The faster that ball is traveling, the more energy you're going to have to apply to make it stop traveling. Those two things are really the only things that contribute to this amount of energy we need to apply to overcome the inertia. Just mass and velocity. Since mass and velocity are both directly proportional to the inertia, then the force required to overcome the inertia must also be directly proportional to mass and volume. That force required to overcome the inertia is what we call momentum. And the way we calculate momentum in physics, we typically use P. Sometimes you'll see lowercase p, sometimes you'll see uppercase P. Just again, you have to kind of take contextual clues when you're doing physics problems. As you've already seen in just this very brief survey and overview of what we've covered so far, we're already running out of letters, right? We're running out of letters to talk about what represents, say, voltage versus velocity. Well, they're both V. A can mean a number of things. So in this case, P, I like to use lowercase p for momentum. Uppercase P has something to do with power. Power is a work per unit time. So our momentum of an object is related to the mass and the velocity. So our momentum, we know that this is kind of related to energy. So let's do a little bit of dimensional analysis here. If momentum is mass times velocity, mass is measured in kilograms. Remember, velocity is measured in meters per second. So we get something that looks like kilogram meter per second. That looks really, really close to the definition of a Newton, which is our measure of force. But our measure of force is dependent on acceleration and not velocity. So the two are very, very closely related, right? The difference is force is ma. It's dependent on mass, it's dependent on acceleration. Momentum is dependent on mass and velocity. So the reason for this is because force is what you're having to apply, right? You're having to create motion by applying an acceleration to an object. Once the object has been accelerated, it has some velocity, right? You've imparted some velocity, change in position per time. And so now there's a different energy there that's required to influence the object. So that's our momentum. I'm going to show you something here that is outside the scope of this course, but I think will help you fundamentally as you begin to transition into higher level mathematics and calculus. The way we think of momentum as advanced physicists is not this standalone equation. Everything that we do in physics is the study of the rate of change of something, right? How something changes with time is our most common thing that we measure. So we look at things like how quickly does something change its position with respect to time, right? So velocity is that position with respect to time, dp dt. Acceleration is the change in velocity with respect to time. So that gives us the quantity we need. There's a quantity called jerk. That is not just the name that they put for me when I teach physics classes next to who the instructor is. There's a quantity called jerk that is acceleration per time. We don't get into jerk too much in this class because we're generally dealing with things that have constant accelerations. If it's not constant, then you can calculate jerk. So this is a clue that kind of everything we do is related to a change in something with respect to time. Let's do something here. Let's take a look at force. Remember, force is mass times acceleration. Well, what does that look like? That's mass. Acceleration our mass does not change with time. So that's a constant. So it doesn't matter how much time passes, the mass is going to stay the same. For a second there. Is the change in force per unit time. Or another way to talk about this is with derivatives. It's our dv dt. Again, outside the scope of this course, I don't expect you to momentum is the rate of change or the derivative of the force vector. Again, really what I care that you know is P equals mv. But I think it's good for you to see where it comes from and why that's true. So what in the hell are we going to do with this? And so what I'm going to do real quick is share my screen. Cars that have hit each other. Now, because momentum is closely related to energy, the thing that we want to keep in mind is that we still cannot violate the law of conservation of energy, right? Energy has got to be conserved because we're not worrying about friction right now, right? Friction is a non-conservative force, and that kind of makes this a little weird. But for now, we're going to talk about frictionless kind of interaction. So energy is a conservative force, therefore momentum must be conserved. So if we take a look at these two cars here, this red one and this white one. So the car has some massive M1. The white car has a massive M2. The first car is traveling at some velocity V1. The second car is traveling with some velocity of V2. We know from conservation of energy that the net force when these two things hit each other has got to be zero. Right? Because we can't create any energy. Well, where is that net force going to come from? Remember, force is related to momentum. So that means momentum must be conserved. So you can see that this first equation here that gives P1 plus P2 equals P total. Remember our lowercase p, that is our symbol for momentum. So this tells us that in this whole system, notice they've kind of circled the two cars. This is our system of interest. So when I talk about systems, I mean the objects that are interacting. Now, in our case, most of the things we do in this class, we're talking about two. And before I was so rudely interrupted by my poor internet, I was saying that we have a total amount of energy in the system. Therefore, we must have a total amount of momentum in the system. So the total amount of momentum in the system, P total, has got to equal to the sum of the momentum that the first vehicle has plus the sum of the momentum the second vehicle has. So let's say they hit each other. Well, what happens now? There are a couple of possibilities, and we're going to talk about both of these in depth. The first possibility is that one vehicle hits the other and they bounce apart. Now, one of them might bounce backwards, it might continue to go forward, but slower, but there's some amount of bouncing off of each other that happens. That's what we call an elastic collision. Think about elasticity like a rubber band. It stretches, it bounces around. The other possibility is that these two vehicles hit each other and they get stuck together. Either because they hit each other really, really hard and became one massive twisted metal, or maybe the bumpers got hooked together, maybe there's an extraordinarily strong glue or magnet or something. Either way, that is the only other possibility, that they become one system, one mass, right? That's called an inelastic collision. Okay, if elastic is where things bounce and stretch, inelastic is where they don't do that. Either way, we're going to have a different set of momentums, right? Car one is now going to have some momentum. Car two is going to have some momentum. The difference here is those momentum values are going to be different because the velocities are going to be different, right? So we can look at this diagram. When the red car hits the white car, they've drawn some kind of ghost images of these cars to indicate motion. And what they're trying to imply here is that after this collision, the red car is going slower, but the white car is going faster because it got pushed. If you go out and play pool, this is exactly what you're doing in pool. You're hitting one ball with another, you're imparting energy, making one ball stop, the other ball moves. On the next lecture, we're actually going to go into some mathematics of that. And I'm going to show you why generally the cue ball stops and the other ball continues moving. For now, let's just understand that there is still a value for momentum. Remember, momentum is only dependent on mass and velocity. If we assume that there was no mass loss on either of the vehicles, right? Nothing came off, nothing got stuck on another car, their masses have to remain the same. The only reason momentum would change is if the velocity changes. In the setup we have here, that's clearly the case. So we call those new momentums. We use this tick indicator up here. We call that prime. So we have P prime, P1 prime, and P2 prime. That, don't get too worried about that annotation. That is just a way that we keep track of the momentums at different times. The reason that we use that notation, again, comes from calculus. When we talk about the rate of change of something, we're talking about something has changed over time. We're talking about a time-based derivative. There is a shorthand in calculus. Instead of writing, like I was putting dp dt, for example, or df dt, instead of writing it that way, you could just say f prime, f with a little apostrophe on it. It means the same thing. That's actually called Newton's notation for calculus. What I generally write with the fractions is called Leibniz notation, because it has to do with the history of calculus. Newton and Leibniz both derived calculus around the same time. And if you ever want to start a bar fight between physicists and mathematicians and chemists, ask them to tell you if Newton or Leibniz notation is better. And somebody's going to fight. To me, I like Leibniz better. I think it's more concise. I think it's easier to follow, because if you start doing these prime things, once you start getting to the fourth, fifth, sixth derivatives, it's really hard to count those things, those little tick marks. But all that to say that when I annotate something as like a P prime or a V prime or something, in this context, generally what I mean is the new momentum of the system after some time, after some change has occurred. Now, we know the energy in the system must be the same, right? We've already established that energy is conserved. If energy is conserved, since energy is related to momentum, then momentum must be conserved. So however much momentum was in the system before the collision has to be the same amount of momentum that's in the system after the collision. So how did we get here? So we notice that we have P1 and P2 before the collision. That's our total momentum. After the collision, we have P1 prime and P2 prime. But that's still got to be equal to the total momentum. So P1 plus P2 has got to equal P1 prime plus P2 prime. Let me go back to the whiteboard. Oh, it already stopped sharing the screen. Thanks. So what I'm talking about here is we have two vehicles. This is our system. Vehicle one has subscripts of one, vehicle two has subscripts of two. So there is some total momentum in the system, P total. The momentum of this first thing is M1V1. The momentum of the second thing is M2V2. We know that P total is just P1 plus P2. After the collision has occurred, stupid internet screwing up again. After the collision has occurred, we're talking about the same system. So P total is the same. But now we have M1, but it's got some different velocity. We'll call it V1 prime. And the second car has some new velocity. We'll call it V2 prime. So P1 prime has got to be M1 V1 prime. P2 has got to be M2 V2 prime. So the total momentum has got to be P1 prime plus P2 prime because we didn't lose anything. But because the total momentum has not changed, that means we can say P1 plus P2 equals P1 prime plus P2 prime. Momentum is conserved. Let's go ahead and do some further substitutions. P1, is M1 V1, P2 is M2 V2. P prime 1 is M1 V1 prime. P2 is M2 V2 prime. So what does this tell us? This tells us that we can now determine what the velocity of the final one of the two cars is after the collision, right? Let's say that we set up a problem where we know, just for example, let's say both cars have the same mass. And let's say that car one is 60 miles an hour. Actually, you know what? We're going to say they're different masses. I don't know what they are, it doesn't matter. Let's say V2 was traveling at 10 miles an hour. So the first vehicle is traveling along at 60, he rear ends this guy that's already going 10. So ultimately what we'd like to find is what the velocities of these vehicles look like. Well, since we want to know velocities, and we already know masses, and we already know one of the velocities, we should be able to find, just using momentum, what's going on. So we just start with our equation for the collision. So we have the vehicle that weighs mass 1, M1. And that's got to be 60 miles an hour plus whatever M2 is, and it had a velocity of 10 miles an hour. That's got to equal to, since mass 1 didn't change, let's say that after the collision, the first car is now only going 5 miles an hour. So its new velocity, V1 prime. M2 is going to be the same. And what we'd like to find out is how fast that second vehicle is going after the collision, right? So we have everything we need to know to solve this. This just becomes algebra, right? So we can say M1 times 60 minus M1 times 5 equals plus M2 times 10 equals M2 V2 prime. Factor out an M1 here. 60 minus 5 gives me 55 plus M2 times 10. And that's M2 V2. So if we divide through by an M2, then we know what our V2 prime is. But we know that, right? This is how momentum collisions are going to work. This is a typical example of an elastic collision. What makes it elastic? Because the two things stay separate. Now, sometimes you can have a system like this, where after the collision, the first car kind of bounces backwards, right? So how do you handle that? The same way we always handle negatives, the same way we always handle reverse, right? That's just the opposite of the direction. We intrinsically chose to the right on the board to be positive. So if to the right is positive, to the left has to be negative. So we just insert a negative sign here. Not a big deal, right? It just makes the math weird. That's all right. So in the end, what you're going to find is you'll get a resultant velocity that may be negative. That's all right. It just means the thing's moving in the opposite direction. Fine. What we're going to talk about in the next lecture is we'll do a couple of examples of this, and then we're going to take a look at inelastic collisions, where things hit each other. We'll do the billiard problem and try to show why the cue ball generally just stops and the other ball continues moving forward. I think that's enough for today. So as usual, if you have trouble, if you need some help, send me an email or come by my office and we will talk about it. So I will see you guys next lecture.